Hello and welcome to our second lesson on important circle proofs. Today, we'll explore two important theorems that will deepen your understanding of how angles behave within circles. Our first theorem is that the angle subtended at the circumference by a semicircle is a right angle. Our second theorem is that angles in the same segment of a circle are equal. After thoroughly understanding these theorems, we will explore various examples to see how these principles can be applied in solving different mathematical problems. In our previous lessons, we familiarized ourselves with terms such as radius, diameter, circumference, and chord. We've also covered some circle theorems, including that the angle subtended by an arc at the center is twice that at the circumference. Finally, we are also familiar with different triangles and their properties. With this solid foundation, we'll now introduce two more circle theorems. Imagine we have a circle and we draw a diameter across it. A diameter, as you know, is a straight line passing through the center of the circle and touching both sides of the circumference. Now let's consider any point on the circumference that lies opposite this diameter. We'll form a triangle by connecting this point to the ends of the diameter. The circle theorem we're currently exploring states that an angle formed at the circumference by this triangle will always be a right angle, which is 90 degrees. So in the above diagram, angle ACB is 90 degrees. Let's look at a few more examples of this theorem in action. First, we have the example we have just looked at for our initial explanation of the theorem. In this case, point C is directly opposite the center of the circle. Second, we have a case where point C is off-center to the left. We can see that in this case, the angle remains a right angle. Third, we have a case where point C is off-center to the right. We can see that in this case, the angle again remains a right angle. So, as we can see, it doesn't matter where on the circumference we put point C, it is always the case that the angle subtended at the circumference by a semicircle is a right angle. Let's now take a look at the proof of this theorem. Let's see how we can prove this theorem. Let's return to our circle with the triangle ABC. Let's also label the radius and connect O and C to form two triangles as follows. Now let's look at the two triangles we've formed, beginning with triangle OBC. Since both OB and OC are radii, we know this triangle is an isosceles triangle. This means two of the angles and two of the sides are equal. Knowing this, we can go ahead and label the angles as follows. Let's now look at triangle OAC. This too is an isosceles triangle, so let's label its angles too. We don't know yet whether they are equal to y, so let's label them x. This leaves us with this diagram. We can simplify the angle at C like this. We also know that the sum of angles in a triangle equals 180 degrees. So x plus y equals 180. Simplifying this, we have 2x plus 2y equals 180. We can divide both sides of this equation by 2 to give x plus y equals 90. So now we know angle C must be 90 degrees, which is a right angle, which is just what this theorem tells us. So this provides the proof of theorem 1. Let's now turn our attention to another interesting property of circles. All angles subtended by the same arc or chord and lying in the same segment of the circle are equal. To see what this means, let's begin with a circle and divide it into two segments labeled 1 and 2 like this. Let's now put 2 points on the circumference of segment 1, and let's label them B and D. We can now form two triangles, first CBE and then CDE. The theorem tells us that angles CBE and CDE will always be equal, no matter where we put B and D, provided that C and E are stationary. Proving this theorem is surprisingly simple. In addition to our diagram above, let's add the center and label it O. We can now draw the triangle COE. In our previous lesson, we learned that the angle subtended at the center COE is twice the angle subtended at the circumference by the same chord. Let's use this theorem to help us with this proof. We can apply this theorem to both of the angles. Let's start with angle CBE. The theorem tells us that if the angle at the center is 2x, then angle CBE is x. We can apply the exact same reasoning to angle CDE. Our previous theorem tells us that if the angle at the center is 2x, then angle CDE is x. Since both of the angles at the circumference CBE and CDE are half the angle at the center, they must be equal. Therefore, angle CDE equals CBE. With these powerful theorems, we can solve many challenging problems involving angles within circles. Whether it's identifying right angles or proving that angles in the same segment are equal, mastering these concepts will be a huge asset in your mathematical toolkit. In today's lesson, we explored two significant theorems in circle geometry: the right angle, subtended by a semicircle, and the equality of angles in the same segment. We began by proving that the angle subtended at the circumference by a semicircle is always a right angle. By drawing a diameter and a point on the circumference to form a triangle, we use the properties of isosceles triangles and the fact that the diameter subtends a 180-degree angle at the center to show that the angle at the circumference is 90 degrees. Next, we investigated the theorem that angles in the same segment of a circle are equal. By drawing a chord and choosing points on the same segment to form two angles, we connected these points to the center and used the property that the angle subtended at the center is twice that at the circumference. This allowed us to deduce that the angles subtended by the same chord are equal. Mastering these theorems enhances our geometric reasoning and problem-solving skills, providing powerful tools for tackling a variety of mathematical challenges.